Welcome back, class. So last time we learned about the losses in the core of the material, which are hysteresis losses and eddy current losses, and we learned about that if the wire is present in a magnetic field and is carrying current I, then the force will be induced in that. Okay, which is actually the cross product of the length of the wire and the present magnetic field. Okay. So, and we also learned that the rate of changing flux, okay, with respect to time, it will induce the voltage in the current carrying wire. Okay, and if you have n number of turns, it will be this. Okay, this is the Faraday's law, or the Lenz's law just represents the sign. So basically now we are going to study the next topic, which is actually the induced voltage on a conductor moving in a magnetic field. Okay, so we have learned that if a wire of the current, for example, this is a magnetic field B into the page, okay, and this is the wire, okay, which is actually moving inside a magnetic field. Okay, so when the wire actually moves inside a magnetic field, okay, with a velocity v, okay, due to some, for example, it got some induced force, and due to that force, okay, the wire start moving towards this direction with the velocity v. So when the wire start moving in the magnetic field, so then what is actually happening? Okay, so this is the magnetic field and this wire start moving towards right. So basically this wire is experiencing the changing magnetic field. Okay, this wire will experience a changing flux due to its movement. Okay, so that changing flux will actually induce the voltage across the terminal of this wire. Okay, that changing flux will induce the voltage across the terminal of this wire. Okay, so that induced voltage, which is actually depending on the velocity, that how, for example, if it's moving faster, the rate of change of flux will be faster. If it is moving lower, the rate of change of flux will be lower. So it will be depending on velocity, it will be depending on the intensity of the magnetic field, that what is the intensity of the present magnetic field around that wire. If it is stronger, lower, it will also depend on that. So induced voltage in a wire moving through a magnetic field, it is represented using this formula. So the velocity cross product with the B, okay, and dot product with the L. Okay, this is induced voltage. Okay, or if we write, it will be VB sine of theta. So theta will be the angle between velocity and magnetic flux density, and it will be dot product with L. Okay, or we can also write this as VB sine of theta into L time cosine of phi. So phi will be the angle between length and the cross product of V and B. Okay, so how we can find the direction of the induced voltage? It's very simple. Okay, for example, if this is the V and this is into the page, okay, so this is into the page B, so you just take the cross product of V cross B. Just curl the fingers of your hand. Okay, curl the fingers of the hand. Okay, so then we know that cross product we get the normal direction. Okay, normal direction which will be upward, the your thumb basically. Okay, so your thumb will be upward, so that will induce that the positive will be here and negative will be here. Okay, for this case I will also explain in more details in the live session. Okay, positive here and the negative here. Okay, so that will be the direction of the induced voltage. So this is basically the basic operation for the generator. Okay, we will learn this in the live session. Okay, this is the basic principle, basically how the generator actually operates. Okay, how the generator converts the energy in the real time. Examples we will solve in the live session. Okay, the last topic of this chapter, this lecture, is linear DC machine. Okay, so we have learned about the basic concepts. Now we are going to combine them together to learn that how basically a basic machine will convert the energy, okay, to different forms. So we will consider this basic linear DC machine, which actually constitutes of a like input battery, a switch, a resistors, and then it have a bar, okay, which is present in a magnetic field, which is into the page cross product. It has a length of L, okay. So basically this is a bar of a conducting metal, okay, like maybe like any conducting metal like copper, okay. So this is just a bar, okay, which is present in a magnetic field, okay. Now basically what is happening, how this machine will start operating, okay, we will see that. So first thing, let's start. To analyze this basic DC machine, we are going to need these four basic equations. The first one is the force, okay. So for example, if you turn on the switch, the current will start flowing, okay. So the current will start flowing, and the current like follow this path, and it will come to this bar, and through this bar the current will start flowing. So if the current is flowing through a bar which is present in a magnetic field, okay, so that bar will experience a force, right? That bar will experience a force. So that force is actually represented using this formula, I times L cross P. Okay, this is the basic formula, that if the current if a current carrying wire is present in a magnetic field, the wire is stationary, okay, that wire will experience a force, okay. So this is the basic first equation, okay, the force on a wire. Now the second equation is, now the because of this force, this wire will start moving, okay, it will experience some velocity, okay. Now what is happening, the wire is moving with a velocity v present in a magnetic field, so it will experience changing flux. So due to this changing flux, voltage will be induced. So second equation will be induced voltage, the terminal of this wire, okay. So that will be v cross b times n, okay. No C here everyone. This is your supply voltage, okay, current is flowing, okay. This is the resistor R, and here we have this bar, and across this bar we have this induced voltage, okay, and the current I is flowing, okay. So basically if it's just supply the simple KVL, so VB will be equal to the drop here I into R plus the induced voltage, okay. If you just write this loop equation, so that will be this induced voltage, okay. So that will be our third basic equation. And the last one is the force across the bar of the tracks, okay. So that will be the net force, which is according to Newton's law will be mass, okay, times acceleration. So for example, this bar is basically present on a track, okay, on which it's moving, okay. So that will also experience some force. So that will be actually our net force, okay, which will be mass times acceleration, okay. So that these are the basic equations which actually determines the operation of the linear DC machine, okay. Now for example, if you want to calculate the current, so current will be, okay, VB, difference of the voltage across the terminals, minus the induced divided by the resistance, okay, that will be the current, okay. So we can calculate the current using this formula, simple formula, okay. Now how the operation will changes, okay, with the changing currents and with the other things, we will see this in the live session in much details, okay. So that is the end of this lecture. Thank you very much for your time.